SwayamPrabha. Digital India. Educated India.
So, this will be lecture number 42 on our ongoing series on mechanical measurements. We are going to look at a new topic in this and forthcoming lecture, that is introduction to measurement of gas composition. There are many situations which occur in mechanical engineering practice. We require to know the composition of gases, as for example shown here, flue gas monitoring. So, if a combustion device is operated, the flue gases are generated in the combustion process, and the health of the combustion system is determined by the composition of the flue gas. If the flue gas contains too much of one or the other component, like for example, if carbon monoxide is present in large quantity, then it means that the combustion is not taking place efficiently, or it is not complete combustion. So, we would like to monitor the carbon monoxide concentration and find out whether the combustion system is functioning properly or not. The next example I can take is the case of atmospheric pollution. Nowadays, the atmospheric pollution has become a very major concern because of the increasing number of vehicles and also increasing population. There are unsuitable or things which are not required are present in large quantities in the atmosphere, and we would like to find out whether these are within the safe limits or not. So, atmospheric pollution monitoring is one of the most important things which we are going to be meeting with in normal day to day practice. Then there are the case of exhaust gas analysis in IC engines, because IC engines are a major producers of these pollutants which ultimately end up in the atmosphere. We would like to find out whether the engine is working properly, so that the exhaust gas does not contain the pollutants in levels which are unsuitable for use. So, basically as you can see, the three examples I have taken are basically because of two. The main reason is that there is a combustion devices which use combustion, and combustion devices are used in production of energy, like in power stations and so on. So, the flue gas monitoring becomes an important activity there, and usually it is done in the stack. Stack is the chimney through which the gases are going to be let out to the atmosphere, and that is where you are going to sample the flue gas. For the second case, atmospheric pollution monitoring, it is present all over the atmosphere along with the air, and we will have to find out how much is the concentration of atmospheric pollutants, and this cannot be done by actually taking an instrument all over the place in the atmosphere and making the measurement. One may have to go for a remote sensing method for this particular activity. In the case of exhaust gas analysis in IC engines, it is possible to do it right near the engine as it is running. For example, it can be done when the engine is running and for example, the vehicle may be moving, or it may be done on a test bed. And many of you are aware of the exhaust gas analysis being done, which is required by law, and you take the car to the pollution monitoring center, and actually he will sample the exhaust gas coming from the tailpipe, and make an analysis and tell you whether it is within the limits or not. So, this is to just have an idea about what are the circumstances in which we are going to make the measurements. So, the next thing I want to look at this briefly, and then I will come back to some of these issues a little later. So, what are the types of gas analyzers? We are going to look at the types of gas analyzers which are used, and broadly we can categorize them into two kinds. One is called separation and the other is called the non-separation technique. Separation technique is where if you have, for example, a mixture of gases, you would like to separate the gases before finding out how much is the concentration of each one of them. So, that means before the measurement a separation of the species is going to take place. In the non-separation technique, it is not necessary to separate them out. The entire gas mixture is sampled and the constituents are measured in the mixed state when they are in the mixed state. So, the separation and non-separation techniques are two main categories. Let us look at the two methods, the non-separation and the separation methods, and look at what are the possible instruments or measurement techniques which are available to us. One is called the non-dispersive infrared analyzer. Of course, we are going to look at it more in greater detail as we go along. It is also referred to as NDIR. It is a very popular method. The basis for this method is of course the using the infrared radiation and its interaction with the gas molecules. So, if you want to measure the presence or absence of the gas or the amount of gas which is present, you will have to make the infrared light pass through the medium where you expect the gas to be present, and based on the measurement you will be able to say how much is the concentration of the particular species in question. We will come back to this in greater detail later. The second technique I can put under the non-separation technique or non-separation method is where you have differential absorption LIDAR. LIDAR stands for light detection and ranging. The differential absorption LIDAR is also referred to as DIAL for short, differential absorption LIDAR. The method is one which uses remote sensing. That means that the measuring instrument is at some location which is not going to change, or it may be on board an aircraft, for example, and the aircraft is moving, and as the aircraft is moving it is going to measure the presence or absence of the gas or the amount of gas which is present, a particular gas of interest to us, by using what is called differential absorption. So, this is the remote sensing of application, whereas the non-dispersive infrared analyzer is usually a stationary one. The third one I am going to look at is chemiluminescence, or which is used for detection of nitrogen oxides. The nitrogen oxides are usually termed as NOx. NOx stands for all oxides of nitrogen which may be present in the particular sample of gas. For example, it may be nitric oxide NO, nitrous oxide N2O, nitrogen dioxide NO2, and so on and so forth. So, usually it is clubbed together in NOx in this term NOx, and the detection of NOx is very important because it is a very highly polluting species which is basically present because of combustion devices. Essentially, for example, the IC engines, gas turbines and so on, they are the producers or the ones which give rise to the presence of NOx in the atmosphere. The second category of methods, the separation method, I am going to take a look at only two methods: the gas chromatography, which is very useful and which is very popular and which is easily available nowadays. In the gas chromatography, of course, we will see later, the species are going to be separated by a certain technique called the chromatographic technique, and the gases which are present in the form of a mixture are separated into its constituents, and these constituents come out of the instruments or come out of the chromatograph column, which we will look at later as in time. The species will come one after the other, and we can that means that they are separated in time, and then we can look at each one of them by various techniques, detection techniques. I will describe it later. The RSAT gas analyzer is a destructive method in the sense that the gas sample is collected and it is absorbed in absorbing media, and then the change in volume is noted, and the analysis is done by chemical separation or chemical absorption method. So, what I am planning to do in this lecture and possibly in the next one is to look at these different methods of measurement and look at the basic principles and also talk about how they are useful and what we can do about them. So, let us look at the typical combustion products. Most of the time we burn hydrocarbons. Fuel is hydrocarbon which contains hydrogen, carbon, and possibly some other things also, like for example some sulfur may be there and so on and so forth. But essentially combustion is of hydrocarbons. Hydrogen and carbon are the most important parts, and the measurement, the combustion is done in air. Air contains nitrogen and oxygen. Nitrogen is coming into the combustion product through the air which is used for combustion, and if the temperature is suitable, nitrogen will combine with oxygen either in the fuel or in the oxygen which is already present in the air. At high temperature they will form some compounds. For example, oxides of nitrogen like NO, nitric oxide, N2O, nitrous oxide, NO2, nitrogen dioxide, etc. They will all form, and they are collectively referred to as NOx. In the combustion product we also will see the most important of course is carbon dioxide, that is what we would like to have, and probably water vapor, because hydrogen is there in the fuel. You expect water to be formed, and water will be the form of steam at high temperature, and if the combustion products are cooled, of course it will condense and water will become liquid water. So, you essentially expect oxides of carbon, carbon monoxide if the combustion is not complete. Incomplete combustion will be indicated by presence of carbon monoxide, and carbon dioxide of course is the product of combustion which will form when the carbon is completely converted to completely burnt and converted to oxide, and then oxides of nitrogen, if the temperatures are proper, suitable, these species will be formed. At high temperatures nitrogen oxide etc. will form, and then of course unburnt fuel, the hydrocarbon which we use as a fuel itself will be present in some quantity, because some fuel may not burn at all. So, the unburnt fuel can also be there. For example, when I talk about combustion product, I can talk about combustion of various types of fuels. It can be solid fuel or liquid fuel or gaseous fuel. So, depending on the type of fuel I am going to use, I may have all these which are mentioned here, or some of these may not be there. It depends on the particular fuel. And of course, there may be particle matter or soot which is actually carbon in the form of particles. It is not completely burnt, the carbon is available in the form of particles, and the presence of particular matter in the form of soot is indicated by the the color of the flame itself. So, that will indicate whether soot is there or not. So, basically what we are talking about is the connection between the presence of the gases in the atmosphere, presence of the gases in the laboratory because of combustion as one of these sources. This is only one of the sources we can think of. There are other sources, as I said. Even humans give rise to a lot of animals also give rise to a lot of gases which are going to be present in the atmosphere. After all, we breathe oxygen and then give out carbon dioxide. It is also known to everybody. Therefore, carbon dioxide present in the atmosphere is because of the living beings, including humans and the animals. And of course, animals also give rise to other gases which are present in the form of methane and so on and so forth. Even vegetation, when it rots or when it when it undergoes slow reaction in the atmosphere, degradation, it gives rise to a lot of these gases. So, the idea is that we would like to monitor or find out what is the amount of these products which are present in the atmosphere, and we would like to look at the various methods which we can use for doing so. For example, we can see the emission limits which are given in this table. This is required by law. These are all the law which is presently followed in India. So, we have the Bharat standard 1, then the Bharat standard 2, 3 and so on. These are the standards which are to be followed by vehicle manufacturers in the design of their vehicle. For example, if I take a carbon monoxide, this is present in the exhaust gas. The limits are specified here in grams per kilometer. So, if you run the car or the engine for 1 kilometer under specified conditions, the amount of carbon monoxide it can emit is limited by these numbers 2.72 and 3.16, and if you look at here the values here, lower values are fire type approval, that means at the stage of the approval of the vehicle, and the higher values for conformity for production. At the production time this can be slightly higher, that is what it means. So 2.7 to 3.16, you see that the amount of emission in grams per kilometer is limited to 2.72, and if you look at the different standards which are being mentioned here, these values are actually coming down. These were the standards available or specified earlier, and now it has come down to 2.2 in the case of BS2, and in BS3 it is going to be more or less the same, but BS4 it is going to be brought down to a level equal to 1.00. Now one may want to know what this grams per kilometer will stand for. So grams per kilometer is measured under specified conditions. If either it can be done by actually running the vehicle and making the measurement, or it could be done by running it on a test bed with the power being produced which can be monitored by using a dynamometer, and then you find out what is the amount of carbon monoxide, which is specified amount, you measure it over a period of time and then relate it to the grams per kilometer. The second thing is hydrocarbon. This is the fuel itself, petrol or diesel or whatever it is, plus the NOx. The NOx is produced during the combustion process. Again it is given in grams per kilometer, and you can see that the values are coming down steadily, and in the BS1 and BS2 the HC plus NOx were clubbed together and we had 0.97, and then it has come down to 0.5, but in the BS3 and BS4 HC and NOx are now separately specified. So hydrocarbons should not be present more than 0.2 grams per kilometer, and NOx is all the nitrogen oxides less than 0.15 grams per kilometer, that is what is specified by this. So you see that the emission limits are specified by law, and in order to meet with these limits we have to design the vehicles properly or the combustion device properly, and in order to monitor we need measurement techniques. So that is how we are building up a case for the need for measuring the gas composition. So let us look at various ways of representing the gas concentration. So I will come back to this slide after I go through a little bit of background. So I am going to look at the various ways of specifying gas concentration. So as you very well can see, there are broadly two ways of specifying it, one on volume basis and the second one on mass basis. Okay, volume basis and the mass basis. So let us look at this. For example, volume basis, I can specify it as so much of a particular gas of interest to us. For example, I can put it the following way. So volume basis is the volume of a particular species divided by the total volume. So I am actually talking of a gas mixture, because seldom are we going to get a condition where the gas is going to be present independently and separately. So we have a mixture of gases, and in that particular gas mixture I would like to find out what is the fraction of the volume occupied by the particular gas. So basically the idea comes from Dalton's law which is very familiar to us from thermodynamics. We have two ways of looking at the gas concentration, either the partial volume or the volume occupied by a particular species in the entire volume, or we can look at it as a partial pressure. We can pressure basis also, it is possible. Of course these two are interconvertible, and generally the volume basis is what is normally used in practice, and it is also represented in a slightly different way. We want to represent it in the following form: ppm volume basis means parts per million This will mean that this will be volume fraction so I am going to just divide by 10 to the power 6. The reason why I am going to take it in the ppm in this particular form is because when we are talking about the presence of gases in the atmosphere or in exhaust gases and so on, the amount is very small. The amount of the gas which I am talking about, for example carbon monoxide, the amount of carbon monoxide which is present in the atmosphere is so small that it is better to divide by this by 10 to the power 6 so that you get in terms of parts per million. So, parts per million will be a whole number, that is the whole point. So, for example 1 ppm volume basis is also like 0.0001% by volume. So, when you are talking about very small quantities, it is better to use a unit which is of the appropriate size, and therefore, I am going to use 1 part per million as a possible use. You saw that pop up menu. So, 1 ppm is also 0.0001% by volume, and the reason why we are using this unit is because we are talking about very small quantities. It is better to talk about you use a unit which is also appropriate, so that the number will be a whole number instead of being a very small fraction. So, another way of if the volume fraction is much smaller than even 1 ppm, we can even have 1 parts per billion, which is represented as 1 ppb, or even smaller. So, it could be 1 parts per trillion and so on and so forth. And the important point to note is that such levels are measurable. With the modern measurement techniques, it is possible to measure such small quantities of volume fraction of gases present in a large volume of gas. The second point I would like to mention here is that the volume fraction is the same as the mole fraction. So, mole fraction or on the basis of mole is the same as, is identical with volume fraction. Now, let us look at how we are going to convert this to the mass basis. So, mass basis. So, this is the second way of representing the presence of a particular gas species, and we would like to find out how to represent. In principle, if I am going to use SI units, this will be simply given by kilograms per cubic meter, just the units of density. So, that means I would like to find out what is the mass of the particular species in unit volume. The unit volume here refers to the volume of the gas mixture. Okay. So, if I am taking 1 cubic meter of the gas volume, what is the amount of a particular species of gas, what is the amount in kilograms which is present in that particular sample. But in practice, as you saw earlier, we were talking about ppm and ppb levels, the amount of the gas present will be very small. So, usually we use microgram per meter cube as the appropriate unit. So, if I am going to represent either on the volume basis or on the mass basis, I can convert from one to the other, and it is very easy to do that. So, I will just give the formula. It is based on ideal gas relation, and if I am given in a parts per in a mass basis, to convert it to ppm volume basis, I will have to just take the value of the mass density in milligrams per cubic meter. Instead of microgram, I am using milligram here, but of course, you can always add one more factor. So, 273.15 plus T in degrees centigrade, because it depends on the temperature, and divided by 12.187 times the molecular weight. So, the temperature is the temperature of the gas sample, the reason why the temperature occurs is because the volume of the gas is to be measured at the temperature which is being prescribed, and at that temperature the volume depends on the volume depends on the temperature according to the ideal gas law. And of course, we are assuming that the pressure is 1 bar. If the pressure is not 1 bar, that can also be corrected by appropriately taking into account, because the linear function of pressure. And the molecular weight is the molecular weight of the species. So, we need to know the molecular weight, and then all we have to do is to substitute here, and we will be able to get the appropriate value. Let me take an example. For example, if I have NO2 and the concentration is given as 20 milligram per meter cube, I would like to find out what is this is the mass basis. So, volume basis, all I have to do is to use that formula which I gave you just now. This will be 20 multiplied by the temperature. If I am assuming the temperature is 25 degrees Celsius, this will be 273.15 plus 25, and this is nothing but your temperature in Kelvin. So, I am just converting the temperature in degrees Celsius to degrees in Kelvin, divided by that factor 12.187, multiplied by the molecular weight is known as known to be 46.01. This is the M for NO2, and this will work out to 10.6. So, the volume basis, it is 10 ppm level, the mass basis is about 20 milligram per meter cube. So, if you are, instead of milligram, if you want to put it as microgram, you have to multiply by 1000. So, it will be 20,000 micrograms per meter cube. It is a rather high level of pollutant concentration. Of course, you can also convert it in the other fashion, from ppm to you can convert to milligrams or micrograms per meter cube, and the same formula can be used for that purpose. And let us look at the mass concentration of various species. If 1 ppm of the particular species is present in the atmosphere, which is at a total pressure of 1 bar or 1 standard atmosphere, and the concentration is going to be 1 microgram per meter cube, you see that the amount of ppm for different species is specified here. For carbon monoxide corresponds to 1145, nitric oxide it comes to 1230, nitrogen dioxide, this is NO2 1880, ozone 1962, sulfur dioxide 220. So, you see the 1 microgram per meter cube, a small amount being present, the parts per million is quite large, as you can see here, and these are the units which are normally used in practice. Now, let us look at what are the various ways of making the measurement of gas concentration. As I said earlier, there are 2 ways of doing it. One is the separation method, the other one is non-separation. Before we go into that, let us look at what could be the types of measurement which could give the gas concentration. So, I have an absorption spectrum of a mixture of gases. So, the absorption spectrum is actually obtained in this case. Let me explain the terms which are used here, very important to understand. This 100 ppm is the 100 parts per million of the gas, the various gases are present in the total atmosphere, and 100 ppm meters means it is the product of the concentration times the path length. Okay. So, how do you take an absorption spectrum? You pass an infrared beam through a certain thickness of the medium, and that stands for this meters. 100 ppm meters can be obtained by have 1 ppm over 100 meter length, or 10 ppm over 10 meter length, or 100 ppm over 1 meter length. So, it can be, this can be obtained by adjusting the concentration times the path length product to 100 ppm meters. So, you can either have very high concentration or a short path length, because they are all equivalent, because when the infrared beam passes through this gas, it gets absorbed. The absorption is selective, and it is depends on two factors, one the wavelength and the other one is the absorption coefficient of the particular species which is present, and different gases are going to absorb in different parts of the spectrum. So, if you look at the screen here, you see that the different species, for example, CO2 is here and CO is here, not very far from it. So, CO absorbs in this band, CO2 absorbs in this band, but if you look at propane and N-hexane, both of them have overlapping absorption. So, they have overlapping absorption. In fact, if I show other gases like water vapor and nitrogen oxides and so on, they will also show some overlap with other species. So, this overlap how we are going to take care of later, we will look at it. And you see the wavelength starts from 3 micrometers. This is the wavelength of the radiation which is passing through the particular specimen or the sample through which the measurement was taken. So, it is from 3 microns to 5 microns. This is the mid infrared range, and the scales are different for other than CO2, this scale is valid, and for CO2 this is valid. Therefore, the CO2 has much more absorption than the other species, as you can see here. But what we are going to notice here is that there is a specific wavelength at which the particular species will absorb, and it will not absorb at other frequencies, other wavelengths. So, that gives me one way of doing the measurement of gas. By using the appropriate infrared radiation of appropriate wavelength, I will be able to select the particular gas which is going to absorb. All other gases will be inactive, that means that they are not going to absorb. I am going to select. So, the separation is not physical, it is separation is done by the wavelength. So, the wavelength will separate the species, it will appear as though for that particular wavelength the other species do not exist. That means that it is non-separation technique as far as physical separation is concerned, but it is separated because of the wavelength. Different wavelengths are absorbed, or radiation at different wavelengths are absorbed by different species, and therefore, if I am interested in CO2, I will use a appropriate wavelength and it will be absorbed only by CO2, other gases will not absorb. Therefore, the whatever absorption I get is related to the presence of the CO2 in the mixture. So, the separation is done by the absorption technique, which is wavelength specific and not physical. So, ultimately we are going to separate out the species, but not physically, but in the wavelength wise. In fact, I have taken this particular sketch from the particular spectrum from this particular the website, and there are more details can be found there. So, what is the use of this particular sketch I have given? The use is to demonstrate that we can do the separation by looking at the spectra using the appropriate wavelength. I can do that. There is one way of looking at this. Another way is it possible that I can do the same thing by a different technique? What do I mean by that? Suppose I want to use the wavelength specific radiation, I have to have a spectrometer, or I have to have a source which will emit only in this particular radiation in this region, for example, if it is CO2. If it is CO, it has to do only in this region. That means I must find a source which is going to be emitting radiation only in that particular wavelength of interest, so that I can do that. That can be done in a spectrometer. In a spectrometer, what we have is a broadband source, or a source which will radiate all over the wavelength scale, but by using the spectrometer we are going to divide the light into its spectral components by some suitable means. For example, I can use a prism, I can use a grating and associated optics, so that I can get whatever wavelength I want, I can get from the instrument. Or I can also use what is called a Fourier transform infrared spectrometer, which will do the separation in a the separation will be done over time. I will come back to that a little later. So, one way is to use a spectrometer. The second way is to use what is the spectrometer, because we are going to separating out the wavelengths into the spectrum of wavelengths. It is called dispersive instrument. So, a spectrometer is a dispersive instrument because the light is separated into its wavelength components. In the non-dispersive measurement, I am not going to separate the light also. I am not going to separate this, but by clever arrangement I will be able to use the NDIR or the non-dispersive instrument to actually measure the presence of the gas by a simple technique. Let us look at the principle which is going to be used in that particular case. So, I use what is called an acousto-optic detector, that is the heart of the matter, and the acousto-optic cell consists of a small cylindrical vessel with a transparent window through which the infrared beam can pass into the cell, and the acousto-optic cell is a volume of gas, and the gas which is contained inside is such that it will absorb the radiation which we want it to absorb. For example, if you fill this with carbon dioxide, it will absorb only the radiation which is absorbable by the carbon dioxide, and the rest will not be absorbed. Okay. And what happens if radiation absorbed by this gas inside? The gas temperature will go up because it absorbs radiation. When the temperature goes up, the pressure will tend to increase. Suppose I have a radiation which is chopped using a wheel with a window. Whenever the window comes in front of the IR source, the radiation will pass through to the acoustic cell. Whenever the window is not there, but the wheel is there, there will be no radiation coming here. So, if you look at the pressure which is monitored by the output of this whatever is shown here, this is a pressure transducer. We have already looked at pressure transducers earlier. It could be a capacitor, for example. So, the capacitance changes, and that will give you a signal, electrical signal. So, when the light is passing into the acoustic optic cell, the pressure goes up, slowly it builds up, and then it reaches a maximum value, and as long as the wheel, as long as this aperture here, there is a hole here, this hole is going to come in and leave. During this process, it is going to be illuminated, and the pressure remains at this value. When once the wheel is, the hole has passed the source, the pressure starts decreasing because there is no radiation communicated here. So, the pressure comes down, and again this repeats itself because I am rotating this wheel by using an electric motor, and the IR source I am going to get a collimated beam here, and that passes through this hole, and I can get an output from this transducer. I can get an output which is going to vary as shown here. So, this is the pressure versus time signal which you get from the acousto-optic cell. In other words, the acousto-optic detector is a detector which detects the radiation of particular wavelength of interest to us. For example, if I want carbon dioxide, I fill it the wavelength corresponding to this region, I use carbon dioxide inside the cell. If I want carbon monoxide, I use carbon monoxide inside the cell, and if some other gas is required. So, the gas contained in the acousto-optic cell is the gas which I am going to detect. So, acousto-optic the cell is also an acousto-optic detector for a particular gas species. Okay. So, that is a very important thing to notice. So, now what is the use of this? So, if I have the following, if I keep in terms of in front of the acousto-optic cell, if I keep a sample cell where I am going to allow the gas sample to go in and out, this is a sample in which I want to find out whether there is carbon dioxide or whatever species I am interested in. So, what happens if you put the sample cell here? The gas of interest to us which is inside in this cell absorbs some of the radiation, and therefore, the radiation received by the acousto-optic detector is reduced because it transmits less than 100% of what is going to fall on the sample cell. Therefore, it is reduced, and therefore, the amount absorbed by the gas which is present here of the particular species which I am interested in. So, suppose I want to measure carbon dioxide in the sample cell. So, this is for some carbon dioxide is here, there is also some carbon dioxide in this cell, and this will absorb whatever is not already absorbed by the sample in the sample cell. Therefore, the output of this acoustic detector will be smaller. You can see that this was the output when there is no gas sample cell or there is no carbon dioxide in this particular cell. If there is carbon dioxide present here, this signal will go down. So, this difference between the signal from this value to this value, that is due to absorption in the sample cell. So, the sample cell, we can find out what is the concentration of the gas in the sample cell by, for example, I can do the following. I can fill the sample cell with a different concentration, known concentration of carbon dioxide, and then I can find out what is the reduction in the signal, and then I can calibrate it. Therefore, I can take standard samples of carbon dioxide of various concentration or mixture containing a certain proportion of carbon dioxide, and I can do this experiment and once for all calibrate the instrument. So, let us look at the thing again. So, without sample, with sample, there is a change in the output of the acoustic optic detector, and what do you notice? You notice that I am using the light coming from the source without converting it to any spectrum. I am using all the light which is coming out. The selective absorption is done by the detector itself. Detector itself is a selective absorber. So, it absorbs only the wavelength of interest to us, and the sample cell, if it contains the same absorber, this carbon dioxide acoustic optic detector will sense carbon dioxide present in the sample cell. So, now let us look at how the NDIR gas analyzer is actually constructed. So, it consists usually of two sources, IR source 1 and IR source 2. We use a reference cell, we use a sample cell, we also use what is called a filter cell. So, the filter cell is an important part of the thing. If you remember, when we talked about absorption, we said several, for example, this is characteristic of carbon dioxide, carbon monoxide, and so. Suppose you take a look at these two, propane and hexane, both are going to absorb in the same region, but to different extent. There may be some overlap, some region where both will absorb, in some region only one will absorb. So, what I can think of is the following. Suppose I put a filter cell in front of the sample cell which contains a large concentration of N-hexane. For example, propane and N-hexane I want to differentiate, or I want to measure the presence of propane when hexane is also present. All I have to do is to use a filter cell with a large concentration of this, so that whatever absorption can take place with hexane will be totally absorbed in the filter cell. So, the filter cell will remove all the radiation which is absorbable by one or the other of the interfering gases, and therefore, what is incident on the sample cell is only the radiation which is not absorbed by both the gases. So, that is how your filter cell is made. The filter cell will consist of the large concentration of the gas which is going to interfere with the particular species in which we are interested in. So, let us see how this NDIR gas analyzer works. So, the first IR source 1, it passes through the filter cell, then through the sample cell, and there is a front surface mirror, so that the radiation is allowed to fall on an acoustic optic detector. This is the acoustic optic detector with a diaphragm in between, and there is a condenser microphone. And now on the other side, the reference cell does not contain the gas we are interested in, therefore, the full intensity is felt here. So, the difference between the pressure developed on this side and this side is actually the output. Though that pressure difference, it is like you remember in the previous case I said with and without sample, with sample and without sample. So, without sample and with sample is not done separately twice, it is done in the same instrument. This is without sample, with sample. So, you have a dual beam NDIR gas analyzer, that means two beams of IR source which are of course matched perfectly, so that they are equal intensity and so on. So, the diaphragm is going to be the communicator between the two parts of the acoustic detector. This diaphragm will deflect, and the deflection of the diaphragm is going to be measured by the electrical output. Of course, the entire thing works with a chopper wheel which is chopping the radiation in the AC mode or alternate current mode. So, the condenser output is also an alternating current or alternating voltage output. So, the magnitude of the voltage output is directly related to the concentration of the particular gas which I am interested in. So, NDR gas analyzer is very popular. It is used for measurement of combustion gases in most in the IC engine laboratories. We have NDIR which is used for CO, CO2 and monitoring these concentrations of various species. But you will also notice that in the case of acousto-optic detector, you require different detectors with different gases being present, so that they can measure the concentration of different gases. So, one detector will not work for all of them. You need 2 or 3 different detectors, so that you can measure the species of different gases if they are present at the same time. So, that is the first example I have taken, the NDIR. NDIR is very popular. It is available in commercially, and it can be set up in any laboratory for making measurements. So, the second system I am going to look at is the remote sensing. So, the schematic of a differential absorption laser system is shown here. Before I discuss this schematic, let me just look at the basic ideas. So, I am going to look at the basic idea of the differential absorption system. What is this differential absorption? So, let us look at the following. You remember we showed the spectrum. The spectrum consists of the following: for any gas, something like that we had. This is a broad band. For a particular gas, for example, I may be talking about CO2, CO, N2O, NO, etc. But if you take this and enlarge, this is also a low resolution spectrum. So, if I enlarge, that means I am going to take a high resolution. It will show something like this. In fact, if you go back to the figure there, you can almost see if you can see here, you see those are all lines here. There are a lot of lines close to each other, and if you enlarge it further, that is what I did just now, that is what I get. So, this has got a large number of lines, close to each other. So, what do we notice? We notice that if you look at the height of this, the height represents the amount of absorption, or in this case the emission. It does not matter which, they are going to be mirror images are the same. Therefore, at this wavelength corresponding to the peak, it absorbs or emits radiation. Okay. And if you go here in the valley, very little of absorption or emission is going to take place. So, I can identify, if I have an absorption band or emission band, something like this, this is the highly absorbing and no absorption or very little. Okay. And this difference here I will say is delta lambda, is very small compared to lambda. It is a very small difference. The wavelength difference between the peak and the valley, this is the peak and this is called a valley, it is very narrow. So, if I have radiation falling on this gas at the wavelength corresponding to the peak, it will be absorbed very highly absorbed, and if the wavelength of the radiation is just a little bit away from that and it is in the valley, it is not going to be absorbed at all. So, differential absorption means choose two wavelengths close to each other, one at the peak, which I will call it as lambda on, each other lambda on close to the peak, this is the peak, and the other one I will call it a lambda off, this is called the valley. So, it is a very interesting technique. So, what I am going to do is I am going to use two beams of light, and in this case I am going to use lasers which are very close to each other in wavelength. That means that lambda on and lambda off are very close to each other. The reason why they should be very close to each other will become clear when we go into more details, which we will do in a little while from now. So, the point is that if the path through the gas is covered by two beams of radiation which are identical in every respect excepting that one has a wavelength equal to lambda on, the other one is going to have a wavelength equal to lambda off, these two are going to undergo different amounts of absorption, and that is why it is called differential absorption. One is absorbed highly, the other one is not at all absorbed, and therefore, by measuring the ratio of these two or the difference between these two, we will be able to find out how much of the species is present in the atmosphere. So, this is just the broad outline of the method, and let us look at the some little bit of how it is going to be actually done. So, I have got a laser source. So, it will have lambda on and lambda off both, and it is going to be leaving the laser, it is going to go, and in the atmosphere I may have some clouds, for example. So, they will reflect the light. So, lambda on and lambda off both are going to be reflected, and I will find out when they come back here, I will find out I have a detector here. So, this is the intervening atmosphere which is full of the gas of our interest. For example, I may be interested in finding out how much of moisture is present in the air, how much of the gas, how much of the atmosphere, how much of water vapor, for example H2O. Of course, in this case when you want to measure the H2O concentration, it is a useful gas because we want water. It is not a pollutant, it is actually a useful thing. So, I want to find out how much water vapor is present in the atmosphere, by measuring, I will choose the two wavelengths such that one of them is highly absorbed, the other one is not absorbed. And the second point, if these two frequencies are very close to each other, the other properties, for example scattering. What is scattering? Because of the particles present in the atmosphere, they may be due to various reasons, we are not going into all those details. The radiation will be scattered, and also when the laser beam goes all the way from the source and gets reflected from the clouds, there are a lot of attenuation because of the beam divergence, then scattering out and so on. So, the scattering and other processes like beam broadening and so on are common to both. because scattering is very highly sensitive to wavelength, but because the two wavelengths are very close to each other, we will take an actual example, you will see how close they are. Then practically there is no change in the lambda. The lambda is, I am talking about very small delta lambda, lambda on minus lambda off. If I do that, it will be very small compared to lambda. That is what we are talking about. This lambda is nothing but the average of the two values. Therefore, because the lambdas are very close to each other, the scattering and other beam spoiling processes are common, and therefore, the only difference between the two will be the differential absorption. So, the only thing which is different is the differential absorption, because lambda on is absorbed highly and lambda off is not at all absorbed. Therefore, if I look at the difference between the two signals which I am going to get, I will be able to find out the concentration of the particular species. And before I just close, I will just give one expression which will be useful. This is called Beer's law, which is valid for small concentration, which is what we usually expect in the atmosphere. We are talking about parts per million and so on. So, if a radiation leaves a point and goes through an absorber and comes out, if this length is L, if the intensity is I naught, the I at L, so we have IL by I naught is e to the power of minus the concentration of the species multiplied by what is called the absorption cross section multiplied with path length. So, this is the concentration that is number per meter cube. This absorption cross section is given in meter squared and the length is in meter, path length in meters. So, in the next lecture we will get back to this particular equation and we will see how this is used for measuring remotely or sense remotely the concentration of species in the interwave atmosphere. Thank you.